Welcome to another Chem 1A lecture video with Professor Brooks. This time we'll be talking about solution concentration. This is to build your skills along the learning objective of differentiating and defining the terms of solute and solvent, and then computing concentrations from known amounts of solute and solvent in terms of the units of molarity, percent concentration, and parts per million or parts per billion concentration. Solutions are homogeneous mixtures of pure substances. So if we're thinking back to our lessons on mixtures, that means we have more than one pure substance in a piece of matter, but we cannot visually see the different types of matter. We often think of solutions as being liquids, but they don't necessarily have to be. Again, a solution is any homogeneous mixture of pure substances. So a good example of a mixture that isn't liquid is our air. Air is a mixture of many gases, primarily oxygen and nitrogen, and you cannot see the different gases that are made, the different gases that air is made up of. They are a homogeneous mixture. Another homogeneous mixture that is not a liquid would be any type of metal alloy, such as brass, which is made out of pure copper and pure zinc in a homogeneous mixture. We can also have solutions that contain more than one state of matter. So having gas dissolved within a liquid, for instance, when we have soda water, carbon dioxide gas mixed with liquid water. The main difference between the terms solvent and solute is the abundance of the different pure substance. We use solvent to describe the material that is in the greatest quantity, and solute to describe the minor contributor in the solution. Solutions can be described by more than simply their constituent solvent and solutes. They are also described by their concentrations, or the relative abundance of solute within the solvent. This can be described qualitatively in terms of whether there is a very, very small amount of solute, in which we would call the solution a dilute solution, as shown on the right, or if there is a large quantity of solute within the solvent, we would say that's a concentrated solution. However, these terms are simply ways of comparing solutions, and to describe a solution more accurately, we need to be quantitative and not qualitative. There are a number of ways in which we can quantify the concentration of solute within a solution. One of the most common units chemists use to describe the concentration of a solution is molarity. As you may infer from its name, it has something to do with moles. In fact, molarity is a unit of concentration that describes a solution based on the number of moles of solute within 1 liter of solution. Molarity is the same as saying moles per liter. So I recommend that whenever you are encountering a math problem involving a concentration in which its units are given as molarity, that you substitute the capital M of molarity for the unit mole divided by the unit liter. This will allow you to more easily cancel out the units as you go through your calculations. It's important to point out that when we're talking about units of concentration, we talk about the amount of solute divided by the amount of solution, not the amount of solvent. In general terms, if the solvent is not specified, then we are dealing with water as the universal solvent. We call these solutions specifically aqueous solutions. In order to prepare a 1 molar solution of sodium chloride, the first step would be to weigh out the appropriate mass of sodium chloride to give 1 mole, so that would be 58.44 grams, and to transfer that solid into a volumetric flask. We would then add an arbitrary amount of water, such as was necessary to dissolve all of the salt. Once the salt was dissolved, we would then continue adding water until we reached the line on our volumetric flask indicating that we contained exactly 1 liter. In this way, you'll note that the total volume of water is likely something less than 1 liter, since some amount of that volume would be taken up by the 58.44 grams of sodium chloride. Another way of quantifying concentration is by percent. Percent simply means per 100. So just like you would calculate your score on a test by taking the number of points that you got divided by the number of points available, and then multiplying by 100 to know what percent you got, we can describe concentration by looking at the mass of the solute compared to the mass of the overall solution. This is what we call mass percentage, and it's described by the unit percent W/W. Now that stands for weight by weight. So this is a really great way about talking about concentrations of solid solutions, because solids are easily weighed out. Another way of using percentage to calculate concentration is when we're dealing with a solution of different liquids. In this case, it's easier to describe amounts of liquids by their volume. So volume percentage would be the amount of solute in milliliters or liters or whichever volume measure divided by the volume of the overall solution times 100%. The third way of describing a percentage concentration is by combining these two concepts for a mass volume percent. This is especially useful when you're talking about the concentration of a solid within water. Water has a density of approximately 1 gram per milliliter. So if we compare the mass of the solid solute in grams to a volume of 100 milliliters of solvent, that's almost the same as saying percentage weight by weight, but we're measuring out the liquid or the water using volume. So percent weight by volume is determined by taking the mass of the solute divided by 100 milliliters of solvent, and then again multiplying by 100 to give the percentage. The final way that we're going to cover in terms of describing concentration is for describing solutions where the solute is in very, very low abundance. And the terms we use for that are parts per million or parts per billion, however is most suitable for the amount of solute in that solution. For these types of calculations, it's important that you ensure that the units used to describe each amount are the same. Simply take the mass of the solute divided by the mass of the solution and multiply it either by 1,000,000 for parts per million or by 1,000,000,000 for parts per billion. One handy thing to remember is that if we consider the density of water once again, remember that I said 1 gram of water has a volume of approximately 1 milliliter. Therefore, if we have 1 milligram of solute, that would be 1/1000th of a gram, or 1/1000th of a milliliter of water in terms of mass. Now, if we use a liter of water instead of a milliliter, we're dealing with 1,000 times greater amount in terms of our volume of solution. So 1,000 times smaller on our numerator and 1,000 times larger on our denominator means 1,000,000 times difference. So parts per million can be quickly calculated when we're talking about mass of a solid per liter of water. Having studied your assigned reading and watched this video, you can now challenge your mastery of this topic by working through this practice problem. Chlorine bleach is a water solution of sodium hypochlorite typically of 5.25 to 8.25% volume per volume. And in this case, we mean the solvent to be water. How many liters of solute are in 1 gallon bottle of the bleach shown below? And you'll note the arrow indicates the concentration of sodium hypochlorite in this particular bottle. All right, good luck. See you next time.